Hello and welcome everyone. Today we're going to take you on a journey of transforming data to information and everything in between. This is a journey powered by digital twins. I'm Volaree, Rendon, Director of Solution Engineering, and I've been in the civil engineering industry for over 30 years, since I was a teenager in fact. Even then, I've been passionate about the natural and built environment, and I entered the civil engineering workforce just as we were making the major shift from manual hand drafting to computer-aided design. With me is my esteemed colleague, Anand, a professional engineer and technical account manager on the solution engineering team here at Bentley as well. So let's first take a look at three major things. One is the global impact of civil engineering. Because civil engineers design and maintain infrastructure which affect public safety globally across diverse regions, and that presents many challenges. We also have to look at the role of professional licensure. Professional licensure ensures civil engineers meet standards, uphold responsibilities, and mitigate risk in their work globally. We also have data accessibility challenges because variations in data access and regulatory frameworks affect how civil engineers perform their daily tasks. So let's step back for a minute and discuss the challenges that we experience as it pertains to data accessibility. Throughout all phases of the project lifecycle, we are gathering raw data and attempting to make sense of it, whether it's data like soil tests, traffic counts, or weather data. Making sense of that data requires an extensive amount of processing, georeferencing, and aggregation before we can even begin to analyze it. Data accessibility presents its own challenge as well, and if the data is incomplete, that is frustrating and time-consuming. This can lead to project delays, which thereby increases costs. Throughout my career, I've always asked myself, if only if I can find a quick and easy way to bring all of that data together. The answer to that question requires us to have the capability to transform all of that information and to contextualize it. In other words, transforming it from raw data into information. Data can only be valuable if it's given context and we can gain insights from it. For example, geotechnical data like soil tests become valuable if you can analyze it in order to determine soil-bearing capacity and foundation design. Traffic data, such as traffic counts, become actionable information so that we can predict future traffic flow and volume in order for us to design proper road capacity. Therefore, transforming raw data into information efficiently depends on the quality and accessibility of raw data for timely engineering solutions. So let's discuss this in more detail. What do we mean when we're discussing contextualization? As engineers, we must apply our education and experience to analyze data within the proper specific requirements and design standards, while understanding the environmental impact, such as temperature and load constraints when interpreting that data. Therefore, data accessibility becomes crucial because in order for us to conduct proper analysis, we need access to historical data, and we need to analyze changes and impacts over time. We need real-time data as well for comparative analysis. This allows us to contextualize the information in such a way that we can make informed decisions and predictions. The next step in the process of data transformation is data organization. This can take many forms. For example, we as engineers organize the data into clear drawings, specifications, reports, and models so we can understand it and make sense of it, and so contractors can understand how to build it. For infrastructure design, we can combine disparate data into comprehensive 3D models so we can look at impacts like utility conflicts, wetland impact, right-of-way encroachment. We can use integrated data platforms to help streamline that process. So once we've acquired, contextualized, and organized that data, we can then analyze it using engineering design and analysis principles. This requires analytical tools to process data and allows us to perform simulations and calculations to assess performance under various circumstances and test scenarios. We also need complete and comprehensive data sets so that we can conduct sophisticated predictive analytics. Finally, once we've conducted engineering analysis of the aggregated, acquired, and contextualized data, we can then gain insights through analytics, using our expertise to derive meaningful conclusions while considering uncertainties and limitations. This, of course, doesn't happen in a vacuum. It requires a team of experienced subject matter experts to communicate their findings, validate the data using quality control procedures in order to maintain a level of trust and reliability. So, how does that relate to the digital twin technology and digital twin platforms? Well, digital twins are essentially the fundamental modeling foundation. You can think of a digital twin as a highly enriched collection of 3D models used to describe a given project throughout its life cycle. And there are several important aspects to the digital twin approach for model-based design and digital transformation. Digital twin models are capable of working with all the various types and forms of project data, not just CAD models and drawings, but geospatial data such as maps, LiDAR, point clouds, and meshes, as well as downstream data like 4D construction schedules, inspection data, and operations IoT data. You don't need multiple systems or interfaces to handle and interact with all these data types. Digital twin models can handle all of it in a single common user interface. With digital twins in a common data environment, we can understand references, workspaces, and standards to ensure that when you are creating models, all the data is included and nothing gets dropped or lost in the translation. Finally, this data, as we all know, is not static. It's continuously being updated. So digital twins in a common data environment provides all the capabilities necessary to easily update and validate our models to ensure that all the stakeholders are working on the most up-to-date information. And you can easily compare model versions and view the complete history and audit trail. Best of all, this model updating process is fully automated. And this is all part of the quality control and data integration process in order for engineers and data scientists to make informed decisions. So to complete the journey from data to information, we need contextual data access. We need improved collaboration, and we need transparent quality control and assurance. And now I'll introduce my colleague, Anand Stephen, to discuss professional liability and ethical responsibilities.
Thank you, Volaree, for taking us along this journey from data to information, and importantly, hitting on key points of interest along the way, namely context of the data, quality control, and transparency behind this the journey from data to information. Before going any further, I'd like to pause here and reflect on the personal liability and licensure that's involved in this transformation from data to information. Here's a brief historical note on how professional liability came into place in the West. Sometimes it's hard to look at an engineer of record who has a lot of social capital and is doing pretty well financially, I would say, to look at it from a sympathetic point of view. Hence, I'd say if we look at their point of view with some empathy, it's important to understand that there's a lot of personal liability at stake in these projects. And often there's very limited transparency in the analog way of project delivery. We civil engineers have been delivering projects for over 100 years with hundreds of years with a robust quality control mechanism in place. Just briefly, what is a quality management system? It comprises of two parts, the quality control and quality assurance. Quality control is the act of performing all the checks by appropriate professionals. Quality assurance, on the other hand, are the artifacts or the proofs that these quality controls measures have taken place. Both of these are important and which determine the liability of the professional licensure that's backing these designs. BC, in terms of time nowadays, as we think of it as before COVID, the idea of data as a resource became quite popular, and rightfully so. In fact, Time magazine, I believe, came out and said data is the new oil. We are at a critical juncture where we can transform these data into meaningful information, and have to do so because we face a lot of challenges collectively to make and build infrastructure and make it viable. Also, crucially, at this particular juncture, we have the potential to transform information back into data downstream. And to be clear, this does not mean elimination of the professional judgment of subject matter experts such as professional engineers and architects. What is important here on the left side, if you look at the graphic, is typically in the analog world, we would collect data, perform data analysis, and backed by the professional licensure, data is transformed into information ready for construction. This is where all the information would die. It would basically be lost in some dusty file cabinet in a basement or an attic. Now, at this juncture, we have the potential to transform this information to data downstream, as you can see on the right side. How can this be done? For this to be done, primarily, you need to have access to the data and information, and importantly, you need to have the data lineage associated with it as well. Now, as Volaree had mentioned before, contextualizing data is important because it's not useful if the data is not meaningful in that particular context and transformed by the appropriate professionals involved. Hence, a geotech engineer transforming soil data is meaningful for construction of foundations. And all these data and information come together in our digital twin platform. What do we mean by that, right? So very simply, when we think of digital twins, it is a combination of assets and processes. In the design space, as I'll show you in the subsequent slides, the assets are various models, plans, specifications, and reports that engineers and subject matter experts produce. The processes on the design side of the equation involve the processes in the quality management system, the various checks that are done within the digital twin environment here, and also the quality assurance, not only the markups with the traditionally in the analog world with various colored pencils or highlighters, but also the trail of these markups, right? That when the issues were created, who they were assigned to, when they were assigned to. These steps provide the assurance that the quality checks were performed. It's also really important to realize that as we move in this digital space, the improved data quality equals lesser liability, because it's really important to know where the data is coming from and how are we going to use it. In a digital twin platform, we have records of the data lineage, where data were produced from, who modified these data, and so on. This obviously reduces the risk in terms of using that information downstream. Risks are directly associated with all kinds of professional liability issues here. And we wouldn't go down to a data source or a library or to look if it was not from valid sources of data to incorporate as research into our projects. Just being silly here, but we wouldn't use a gossip magazine or a tabloid magazine as a source of ownership information of property. We have to go to the appropriate data source to get that information. Digital twins enables us to bring that data source in and also have appropriate data lineage information in there. Along with data accessibility, we are able to maintain the same ethical standards that we have been maintaining over hundreds of years, which is backed by our professional licensure. We are not throwing the baby with the bathwater. The rigor of quality control will be continued to be maintained. And towards the end, as Volaree was speaking, she had spoken about maintaining trust. This is critical in our industry because the end product, while it might seem counterintuitive for me, working for a software vendor, is not the model. It's not the CAD model. It's not the specification or the report. For all of us in this industry, the ultimate end product is that sidewalk, that bridge, that improves the lives of our fellow citizens. So it is that critical piece of infrastructure that enables and empowers our citizens to live a better life in this world. Hence, we must maintain trust as we build these pieces of infrastructure. Now, I had mentioned the process. For a digital twin, you have processes and you have assets. In the design side of the equation, as I had mentioned, is bringing together the processes of quality control that have backed our industry. While it might seem painful while we're performing it is crucial to bring that forward to maintain the trust. We can expedite the process as we move in the digital space. Not only that, we could increase the level of transparency by clearly documenting and providing a trace of various quality control measures that have taken place, thereby improving quality assurance. And all this happens within the digital twin platform. Now, from the perspective of the engineer of record, typically in the analog space, they did not have a lot of insight as the issues were getting resolved. But within the digital twin platform, multiple stakeholders can visualize the issues and various steps in the quality control that are being undertaken as the project progresses. Here's a very simple, straightforward example in the representation of the asset. The model has been designed, we bring it into the digital twin. That is the asset that's coming into the digital twin. A digital twin has more than spatial data when you're looking at it from the design point of view. Of course, you have the models and various documents with spatial information. Critically, you have non-spatial data such as documents, reports, schedules. Also, we have other stakeholders, the general public for outreach. These all are part of the project delivery and can be brought into the digital twin and critically managed from that platform. And that's how we bring everything together into one platform to improve the quality management system, reduce the risk, and help the professional engineer deliver projects as they transform data into information. Thank you all for joining us in this journey of transforming data into information. Thank you.
Thank you.